In this video, we will discuss the solutions of the midterm exam on probability and statistics course taught in spring semester 2018. The exam contains two parts. The first part contains 10 questions where the students need to answer the questions shortly and briefly describe the answers. And the second part contains 7 problems where the students need to solve them. So the first problem is about the binomial distribution and calculating the expectation of the binomial distribution. The second problem is about the rules of probabilities, like a rule of total probabilities, multiplication rule, the Bayes theorem. The problem number 3 is about the discrete random variable with a given probability distribution table, and the students in this problem, students need to understand the distribution table. And problem number 4 is about the continuous random variables. So it is about how to evaluate the probabilities and conditional probabilities for the random variables which are given with some density functions. Problem number 5 is we're given the table of the distribution. We need to calculate the expectation of some function of the random variable. Problem number 6 is about the Poisson distribution and the exponential distribution and their relationship between them. And the problem number 7 is a bonus problem. In this problem, students are required to write the pseudocode of the two functions. The first function is the Bernoulli trial. It should give me 1 or 0. Depending on randomly. And the second problem is the students need to write a pseudocode of the binomial distribution or binomial simulation. So let's go through all the problems one by one. So the first part of the exam contains 10 questions. Let's go through all the questions. So we take one card from the standard deck of cards, and this card is red. We know that this is red already. So what is the probability of choosing the kings? So our sample space contains 26 cards, 26 of all the red suited cards, right? So among them there are 2 kings. So king hearts and king diamonds. So probability of choosing one of the kings from the red cards is equal to the 2 over 26 or simply 1 over 13. So in this second problem, we need to calculate the standard square. So we're given the mean is equal to the 15, standard deviation is equal to the 5, and the x, the point, is given as 10. So we need to calculate the standard square for this x, which is x minus mean divided to the sigma, or 10 minus 15 divided to the 5, which will be equal to minus 1. In the next problem, we need to calculate the probability of the complement of the event. This is equal to the 1 minus probability of the A. 1 minus, so this is given 0.6, so that is why it will be 0.4. Problem number 4 is about calculating the simple probabilities. We're given the box with 12 chips, and we need to evaluate the probability of choosing the white chip. So this is equal to the number of the white chips divided to the total number of the chips, which will be 1 over 3. Problem number 5 is about calculating the expectation of the discrete random variable. So discrete random variable x takes the values 0 or 1 with the corresponding probability 0.3 and 0.7. So the mean of this random variable, or the expected value, is equal to the 0 multiplied to the 0.3 plus 1 multiplied to the 0.7, which is equal to the 0.7. Problem number 6 is about combinatorial analysis. So we need to permute the letters of this word. So there are 7 letters in total, and permutation of the 7 different letters is equal to the 7 factorials, but since there are 2 R's, we need to exclude the cases when they permute them. So the number of the cases when we permute them is 2 factorials. So that is why the number of the permutations of the 6 letters when 2 of the letters are alike is equal to the 7 factorials divided to the 2 factorials. In the problem number 7, we're given the random variable was its corresponding density function. We need to evaluate the expectation of this random variable. So this is equal integration from 0 to the 1, because the density function is non-zero only in this region, of the density function multiplied to the x dx. So this will be integration from 0 to the 1, x multiplied to the 2x dx. After I find the antiderivative of this, it will be 2x cubed over 3. And we need to evaluate this at the 1 and 0, so this will be 2 over 3. Problem number 8 is about the negative binomial distribution. We roll a die, a standard fair die. Probability, so we consider the success is when we get a 6. Probability of success in this case, it will be 1 over 6 then, because like, yeah. And we need to evaluate the probability. So we stop this case, so we start rolling a die, and we stop rolling this once we get the third 6. So the number of successful trials should be 3, and we're required to find the probability of having third successful trial on exactly 5th trial, right? So n should be equal to the 5, and we need to use the formula of the negative binomial distribution. This is combination of the 4 and 2, p in the power of 3, q in the power of 2. So if we simplify out everything, we'll get 6 multiplied to the 1 over 6 in the power of 3, 5 over 6 in the power of 2. Problem number 9, student has to sell 2 books from the collection of 6 maths books and 4 economics books, right? So let me call them Maths 1, Maths 2, Maths 3, Maths 4, Maths 5, and Maths 6, and Economics 1, 2, 3, and 4. So what are the different choices of books from different subjects, right? So we need to just make the pairs, right? So N1 can be paired with all of the 4, right? E1, E2, E3, and E4. The same way we can make 4 pairs for M2, M3, M4, M5, and 6. In total, the number of the pairs will be equal to the 4 multiplied to the 6, right? Or 6 multiplied to the 4, 24 different options. In the problem number 10, we're given the random variable with its binomial distribution. We need to evaluate the probability of this random variable takes the values less or equal to the 2. This is equal to the sum of the probability when x takes a 0, or 1, or 2. So probability that x is equal to the 0 is the combination of 4, 0, probability of success is 0, probability of failure is 4. So this will be simply q in the power of 4. Probability that number of successful trials will be 1 is c for 1, p1, q3. This is 4 multiplied to the p, q in the power of 3. Probability of having 2 successful trials, it will be c for 2, p in the power of 2, q in the power of 2, or simply 6 multiplied to the p squared, q squared. That's it with the first part. Let's start with the second part. The first problem, a biologist has a culture consisting of 13 cells. In a period of 1 hour, independently of other cells, there is a probability of 0.4 that each of these cells splits into the T cells, right? So in the first problem, we need to evaluate the probability of having more than 16 cells after 1 hour. Right? So let's say x is our random variable. This will not be the number of the cells in total after 1 hour. So this will be the number of the additional cells, right? Split cells is the number of additional cells after 1 hour. So initial 13 cells is there after 1 hour. So x may take the values from 0 to the 13, right? So x has the binomial distribution with n 13 and probability of success 0.4, right? For each of the cell, we have like considered success if it splits to the 2, and failure if it doesn't split to the 2, right? Either 1, either 0. So either additional cell on the chosen cell or no additional cell. Probability of having 16 or more cells after 1 error, so this is calculating the probability that number of the additional cells will be more or equal to the 3, which is 1 minus probability of x is less than 3 or less or equal to the 2. So we need to evaluate probability that number of the additional cells will be 0. This is C 13 0, P 0, Q in the power of 13, or simply Q in the power of 13. Probability of x is equal to the 1. This is C 13 1, P in the power of 1, Q in the power of 12, or simply 13 P Q squared, or probability of x is equal to the 2. This is C 13 2, P squared, Q 11, or simply 6 multiplied to the 13, P in the power of 2, Q in the power of 11. Please note that you don't need to calculate all the answers, so this is enough to leave the answers like this. In a B part, we need to find the expected number of the total cells after 1 error, right? If x has a binomial distribution, then the expected number of additional cells will be n, which is 13, multiplied to the p, which is 0.4, so this will be 5.2. And the number of the total cells will be 13 plus 5.2 is equal to the 18.2. So after 1 error, we expect that there will be 18.2 cells in total. Problem number 2. So there are 2 boxes, box A and box B. So the first box contains 6 red balls. The second box contains 5 red balls. The first box contains 5 blue balls, and the second box contains 6 blue balls. So we toss the coin, and if heads is obtained, we choose 3 balls from the A. If the tails are obtained, we choose 3 balls from the B. And put them to the jar. So in the first part, A, what is the probability after we choose 3 balls to the jar? So the jar contains 2 red balls and 1 blue ball. What is the probability of choosing 2 red and 1 blue balls? So we can get the 2 reds and 1 blue either from the first box, right? So probability of having 2 red and 1 blue either from the box A, multiplied to the probability of choosing the balls from the box A. Or we can get the 2 red and 1 blue from the second box, box B, multiplied to the probability of choosing box B. So this will be equal to, so let us evaluate, what is the probability of choosing 2 red balls and 1 blue ball from the first box. So let's assume that we choose the balls one by one without replacement. So probability of choosing the red ball in the first time is 6/11, right? 11 balls in total initially, multiplied to the 5/10 because like we choose 1 ball previously and we didn't put this back, multiplied, and in the last we need to choose 1 blue ball, which will be 5/9. And we have to multiply this to the probability of choosing the box A, which is 1/2, plus what is the probability of choosing 2 red and 1 blue from the box B. So this is 5/11 multiplied to the 4/10 multiplied to the probability of choosing 1 blue. At the end, it is 6/9 because 9 balls left on the third trial, multiplied to the 1/2. So on a B part, so if the jar contains already 2 red balls and 1 blue ball, what is the probability that we chosen those balls from the box A, right? Or we obtain the heads when we toss the coin. So this is the probability of choosing the box A if we know that the jar already contains 2 red and 1 blue balls. So using the base rule, we can write this as choosing the 2 red and 1 blue balls from the box A multiplied to the probability of choosing the box A divided to the probability of choosing 2 red and 1 blue balls. So this will be equal to the 6 over 11, 5 over 10, 5 over 9 multiplied to the 1 over 2 divided to this number which we have already calculated previously. So 6 over 11, 5 over 10, 5 over 9 multiplied to the 1 over 2 plus 5 over 11, 4 over 10, 6 over 9 multiplied to the 1 over 2. Problem number 3 is about the discrete random variable and its probability distribution table. So we're given the distribution table and we're missing all the t-values here. So what is the probability that random variable x takes the negative values, right? So in this case, I see that the probability of the x squared is equal to the 1. It means like probability of x squared is equal to the 1 means probability of x is equal to the minus 1, or probability of x is equal to the 1, right? Or we can substitute this or with the plus sign. So we're given the x squared is equal to the 1 is equal to the 0.1. So since probability of x is equal to the 1 is equal to 0.05, this should be also 0.05. We're also given that the probability of x squared is equal to the 4 is 0.3, right? So x squared can be 4 if x is equal to the 2, or we can substitute this with the plus, x is equal to the minus 2, and this should be equal to the 0.3. So if this one is equal to 0.2, then this one is equal to the 0.1, right? So probability that x is negative is x is either minus 1 or minus 2. So probability that x is minus 1 is equal to the 0.05, and probability that x is equal to the minus 2 is equal to the 0.1, so the answer is 0.15. Let's go to the problem number 4. In this problem, we need to calculate the probabilities for the continuous case. So x has the uniform distribution in this interval. We need to evaluate this probability. So first of all, we need to get the density function. So the density function of the uniformly distributed random variable is equal to 1 over b minus a. So b in our case is 1, a in our case is minus 1. So this will be 1 over 2 if x is in between minus 1 and 1 and 0 otherwise, right? So probability that x is in between 3 over 4, less than 3 over 4, if it is already given that x is more than 1 over 4, is equal to the probability that x is in between 1 over 4 and 3 over 4 divided to the probability that x is more than 1 over 4 according to the base rule. Right? So let us calculate each of the probabilities. So probability that x is more than 1 over 4 is equal to the integration of the density function in this interval, right? So this interval is from 1 over 4 until infinity, but since the density function is equal to the 0 for all the regions where x is more than 1, so it's enough to integrate this until 1 only. So this is equal to the integration of 1 over 4, 1, f of x is equal to the 1 over 2 dx, right? So this will be 1 over 2x, 1 over 4 and 1. So if you put 1 and 1 over 4, you'll get we'll get 1 minus 1 over 4 multiplied to the 1 over 2, or simply 3 over 4, 3 over 8. Right? So in a second one, so we need to evaluate the probability that x is more than 1 over 4 and x is less or equal than 3 over 4. Right? So this is equal to the integration of the density function between 1 over 4 and 3 over 4 dx. So this is equal to 1 over 2x, and the 3 over 4 and 1 over 4. If you put the values and calculate this, it will be 3 over 4 minus 1 over 4 or 2 over 4 or 2 over 8, right? So then the probability that x is less than 3 over 4 given x is more than 1 over 4 is equal to 2 over 8 divided to the 3 over 8 or simply 2 over 3. Let's go to the problem number 5. So this is like simple calculations problem. So we're given the random variable with the following density function, distribution function. We need to simply calculate the expectation of the x multiplied as x plus 2. So let me first of all open up the brackets inside the expectation. So this will be x squared plus 2x, or simply expected value of the x squared plus 2 multiplied as expected value of the x. So let's calculate the expected value of the x first of all. So this is like every output of the random variable multiplied to its corresponding probability, and we need to sum them. So this is equal to the 1 plus multiplied to the 0.2, 2 multiplied to the 0.2, 6 multiplied to the 0.2, and so on. Or I can just write this 1 plus 2 plus 6 plus 4 plus 5 multiplied to the 0.2. If we sum this, we'll get 18 multiplied to the 0.2 or 3.6. So in order to calculate the expectation of the x squared, so we need to square each of the output and multiply this still to the corresponding probability. So this will be 1 squared multiplied to the 0.2 plus 2 squared multiplied to the 0.2 plus 6 squared multiplied to the 0.2 plus 4 squared multiplied to the 0.2 plus 5 squared multiplied to the 0.2. What we'll get 16.4. So the expectation of the x squared plus 2 multiplied to the expectation of the x will be equal to the 16.4 plus 2 multiplied to the 3.6. So this is equal to the 16.4 plus 7.2 or simply 23.6. The problem number 6 is about the exponential distribution and the Poisson distribution. So the A part is about the Poisson distribution. So calls arriving to the ratio was the Poisson distribution was the mean 5.2 calls per minute, right? We need to evaluate what is the probability that more than 5 calls will arrive to the ratio in 1 minute, right? So this is equal to the 1 minus probability of x is less or equal to the 5, or simply 1 minus p of x is equal to the 0, and the sum until p of x is equal to the 5. So we can evaluate each of the probabilities 0, 1, 2, or 3, 4, 5 using the Poisson formula. So probability of x is equal to the k, for example, is equal to e in the power of minus lambda multiplied to the lambda in the power of k divided to the k factorials. For example, probability that x is equal to the 0 is e in the power of minus lambda multiplied to the lambda in the power of 0 divided to the 0 factorials, or simply e in the power of minus 5.2. Right? And probability of x is equal to the 1 is e in the power of minus 5.2 multiplied to the 5.2 in the power of 1 divided to the 1 factorials, or simply 5.2 multiplied to the e in the power of minus 5.2. So we can evaluate all of the things there and put them to here. So the B part is about the exponential distribution. So what is the probability that a waiting time between the two consecutive calls will be less than 10 seconds, right? So in order to calculate this, we need to use the formula. So the cumulative distribution function for the exponential distribution is equal to 1 minus e in the power of minus lambda omega, right? So here, note that this lambda should be scaled in seconds if we would like to do this in seconds, or we need to calculate this probability in minutes, right? So omega is less than 10 seconds is actually 1 over 6 minutes, right? So 1 over 6 minutes. So this will be equal to, according to this formula, 1 minus e in the power of minus 5.2 multiplied to the 1 over 6. So e 1 minus e in the power of minus 2.6 over 3. So we can leave the answer like this. So in the problem number 7, we need to write down the code of the procedures. The first procedure should give us the x, either 1, either 0, for a given probability of success, right? So here we can use the random generator. Here the function ran gives us the values between 0 and 1 randomly. So let's write this. So x is the function called Bernoulli, was the input p. So first of all, we need to generate the random value between 0 and 1, some random variable between 0 and 1. And if this random value is less or equal to the p, which is also between 0 and 1, then we get x to be equal to the 1. And if this is more than p, we put x to be equal to the 0. That's it. So we'll finish the end, if, and the function itself. Second procedure is, so we need to simulate this, right? So as in tossing the coin. So we toss the coin, every time we've got a success or the failure. So we can simulate the success or getting failure using the Bernoulli function. And we just need to count the number of the ones we get after the Bernoulli function. So m is equal to the binomial function with inputs n and p. So we start in the beginning m to be equal to the 0. So this is number of the successful trials when we do our trial, like our experiment n times. So we need to write the loop for I from 1 to the n. So every time, in every time of the loop, we need to call the function Bernoulli. And we just need to count the number of the successful trials, right? Or basically, we need to increment the m when we have the x to be equal to the 1. And if the x is equal to the 0, so we don't add anything for the m. So, and that's it. So this m returns us the number of the successful trials when we do our experiment n times. That's it.